In this lecture, we're going to look at the learning outcomes which are associated with the practical work we carry out for the organic synthesis section of the course. There are four main stages to most organic synthesis: preparation of your product, the isolation and purification of your product, identification of your product, and then any associated calculation, most commonly percentage yield calculation. So in this lecture I'm going to look at each of these four sections in turn, starting with the preparation. Now, preparation is probably the simplest part of the process, and the only learning outcome there is that you should be able to explain the theory of refluxing, because very often to make a product we have to heat up the reaction mixture, and being organic chemistry, normally some of the reactants, or indeed the products or byproducts, are very volatile. So if you have to heat them up, you tend to get a very low percentage yield because you lose your reactants or products by evaporative losses. Now, one way around this is to do it in a sealed vessel so the gases can't escape, but in that case you're likely to get an explosion. So the way around it is to reflux the sample. So we'd have the reaction mixture in a round bottom flask. We'd normally heat it up using a heating mantle, as that gives you a very controlled temperature and it's a lot safer because you don't have a naked flame. But you're still going to get the volatile reactants or products evaporating. But on top of the round bottom flask we've got a condenser. So the gases that are formed as they go up the condenser will cool down before they escape from the top. So they'll cool down and condense back into a liquid and drop back down to reaction mixture, hence minimising any losses due to evaporative losses. Okay, so we've heated our sample heated our reaction mixture for half an hour. We've made our product. It's in our round bottom flask, mixed up with our unused reactants and other products. And so the difficult and clever part in organic synthesis is then to get our product out of here and purify it. So we move on to the isolation and purification stage, and there's probably four main techniques we can use to isolate and purify our product from the reaction mixture. First one is simply filtration. Now, the theory behind filtration has not changed since S1. So if our product happens to be a solid, we can then filter it out of the reaction mixture. The only thing that has changed at Advanced Higher was the equipment we used. So Advanced Higher, we tend to use a Buchner flask, which has got a side arm which is connected to a water pump to provide a vacuum in here, which will pull the reaction mixture through the Buchner funnel and speed up the filtration process. So here's our Buchner flask, and here's the Buchner funnel that we use for the filtration. Okay. The second method we often use is distillation, and again there's been no great new theory behind distillation. We came across it in S3, but you should be able to explain the theory of distillation. So basically we use it to separate liquids with different boiling points. So the classic example would be separating ethanol from water. Ethanol boils at 80, water 100. Heat the sample up to 80, the ethanol will boil, turn into a gas, then gets condensed here, turns back into a liquid, and we can collect the distillate in this receiving flask. Occasionally Advanced Higher, we have the receiving flask surrounded by ice, again just to reduce evaporative losses. The next two methods for isolation and purification are new to Advanced Higher though, and these are two very important parts of the course. First way is solvent extraction, and you should be able to explain how solvent extraction can be used to separate and purify reaction products. Right, imagine this red solvent here, this red organic solvent here is our reaction mixture, and let's just say the black dots are our products and the green dots are impurities, unused reactants or other products that we want to get rid of. So in solvent extraction, we add in, if that's an organic solvent, we'd add an aqueous solvent, and we use a separating funnel which looks like this. We then mix it up, okay, so we get a good mixing between the two solvents. So this is it mixed up, and then if you clamp it and leave it to settle for 5 or 10 minutes, the two separate layers will reform. And if we've wisely chosen our solvent, we can get a situation where the black dots, which is the product what we wanted, all go into the aqueous solvent, and all the impurities which we don't want stay in the organic solvent. So we then just run off the organic solvent, throw it away, and we've got our isolated, purified product. Of course, it could be the other way around, you know, the green stuff's what we wanted and the black stuff's what we want to get rid of. So, very simple, works really well as long as you choose the right solvent for your extraction. So the crucial thing is choosing the solvent. So what do you need to consider when choosing what solvent? Firstly, you want to consider the miscibility. So miscibility is when two solvents mix together. We don't want that to happen. We want the solvents to be immiscible. So they don't mix, they form two separate layers. Now, in this example, the organic layer is the bottom layer, the aqueous layer is the top. That won't always be the case. That would just depend on the density of the two solvents. The more dense solvent will be at the bottom. If your solvents have got very similar densities, you might not get very good separation. And one way around that is we can always increase the density of the aqueous solvent. The aqueous solvent is usually just water, but if we add salt to it, so we get a saturated solution of sodium chloride, that increases the density of the aqueous solvent, and we can do that in situations where the aqueous and organic solvents have similar densities. Okay, so pick two solvents that are immiscible and form two distinct separate layers. But also of great importance is considering the solubility of the compound that we're wanting to extract in the solvent. So in this case, we were wanting to get the black stuff into the aqueous solvent. So we wanted to make sure that the black stuff that we wanted was really soluble in the aqueous solvent. And given the choice between the aqueous and the organic solvent, it'll go into the aqueous solvent. This is an idealized example up here. It would be very unusual for 100% of your desired product to go into one solvent. It usually partitions between the two solvents, say in a 90% to a 10% ratio. So in one extraction, you'd be doing really well to get, say, 90% of your desired product in the solvent you want. So again, this is a place where you can get losses. One way around that is to do several extractions. So if you get 90% out with your first extraction, do another extraction and you get another 90% of the remaining 10% out. So in fact, when you do solvent extraction, it's more efficient to do several small extractions than one large one. So if you're going to use, say, 50 mils of solvent, doing two extractions of 25 mils, you'll get more out than doing one extraction with 50 mils. And the last thing you need to consider about the solvent is you need to make sure there's going to be no reaction between the solvent and your desired product. So with good choice of solvent, one that gives you two immiscible layers, one in which you get a high percentage of your desired product going into one of the solvents, and there's no reaction between the solvent and your product. Solvent extraction is a very efficient way of isolating and purifying the sample. Okay, the final method, again which is new to advanced hire, is recrystallization. And it's important that you can explain how recrystallization can be used to separate and purify your reaction products. We tend to use recrystallization when you've got an impure solid. So here I've got my impure solid. The red dots are the product I was wanting to make. The green dots and the blue dots are impurities. So what we do is we dissolve the sample in a hot solvent. So the red dots, which become from closed to open, so our desired product dissolved in the hot solvent, as did the green dots, but the blue dot was insoluble in the hot solvent. So if we then filter it, the insoluble impurity, the blue dot, is removed. So we've got rid of one of our impurities, but we've still got the green impurities in there. We've then allowed the filtrate to cool. If you've chosen your solvent wisely, then your desired product will recrystallize out from the solvent as it cools down. But the green impurities, being so soluble in the solvent, stay dissolved in it. So we then filter off our desired product and get rid of the soluble impurities. So it's a very clever way of getting rid of both the insoluble impurities and the soluble impurities. But once again, a bit like the solvent extraction, it depends on the wise choice of solvent. So what do we have to consider in our solvent choice? Right, the product, so the red stuff in this case, should have a high solubility in the hot solvent. Okay, so it dissolved really well in the hot solvent, but should be virtually insoluble in the cold solvent. So insoluble in the cold solvent. And our impurities should either be insoluble in the hot solvent, like the blue dots, or completely soluble in the cold solvent, like the green dots. So with a good choice of solvent, this is a great way to do a fairly high level purification of your sample. And finally, of course, as before, the product should not react with the solvent. So with careful choice of the solvent, we can get rid of both the less soluble and more soluble impurities in the sample, leaving ourselves with a nice pure product. Okay, so that's the hard work. We've prepared our sample. We've then isolated the product we wanted from the reaction mixture and purified it. Next, how do we know how good our purification process was? Have we made and purified what we wanted? One way of assessing that is by doing a melting point analysis. Okay, so you should be able to explain how we carry out a melting point analysis. So we get a small part of our sample and put it into a very thin-walled capillary tube, which we then place into our melting point apparatus. The melting point apparatus has a big metal block which gradually heats up, and we can see at what temperature the sample starts to melt and at what temperature it's completely melted. So if we've got a pure sample, it should have a very small melting point range, 1 or 2 degrees at the most, and it should be close to the expected value, because we can look up a book and see what temperature our aspirin, say, should melt at. If there's impurities in our sample, it lowers the melting point and lengthens the range. So if we are wanting our aspirin to melt at 120 and our sample melted between 105 and 115, that would suggest it was quite impure. Okay. Now, when carrying out melting point analysis, it's crucial that the temperature is rising very slowly at the critical point round about the melting point. If you have the temperature rising too quickly, you get an effect very similar to this. Okay, so heating the sample too quickly has a similar effect to having to, it can make it seem as if you've got impurities in your sample when you don't. Because the temperature is being read from a thermometer with a very thick glass wall because it contains mercury. So the temperature being recorded by the thermometer lags a little bit behind the temperature being experienced by the sample in this very thin-walled glass tube. Now, if the temperature is going up very slowly at the melting point, the difference, that the thermometer will be more or less at the correct temperature. But if it's going up too fast, the temperature of the thermometer will lag behind. So that although the sample is melting at 120, where we want it to melt, the thermometer might still be reading 110 because it's lagging behind because of making it go up too fast. So it's important the temperature is rising very slowly, about 1 degree a minute, round about the crucial melting point range. Right, a second quite clever thing to do is a mixed melting point analysis. Okay. So we use a similar setup, only in the sample we have a 50-50 mixture of the product that we've made and a pure sample of the product we've bought in. So we get a 50-50 mixture of them, grind them up and put it into the melting point tube and carry out a melting point analysis as before. Now, if the melting point is sharp and close to the expected value, the identity of the compound will have been confirmed. So you're only going to get a sharp melting point close to the expected value if what you've made is spot on. Again, let's work with the aspirin example. If our synthesized aspirin is identical to the bought aspirin. Now, again, let's just think, well, the pure aspirin melts at say 120. I'm not sure if aspirin does melt at 120, I'm just making that figure up. And the product we've synthesized melts at 120, so we get a good sharp melting point at 120. But you may wonder, what happens if what we've made isn't actually aspirin, but it does still happen to have a melting point of 120? Would we not still get a sharp melting point at 120? The answer is no, because what we've synthesized, X and aspirin, if they're not the same, they act as impurities for each other. So the melting point would be depressed, it would be lowered, and the range increased. So even if both samples melted at, both products have a melting point at 120, the fact that they're different from each other lowers the melting points of them both. So had the compounds not been the same, the melting point would have been much lower and the range broader, because each compound would act as an impurity for each other. So a sharp, close, mixed melting point analysis confirms that you've got what you think you're making. And finally, the last way to assess the purity of your product is by thin layer chromatography. So we dissolve a small amount of our product in a solvent and dot it onto a chromatography plate. Put it in the solvent and leave it for a few minutes to allow the solvent to come up the thin layer plate, and we take it out before the solvent reaches the top of the plate. And as it moves up the plate, it will separate the compounds in this spot depending on the solubility of the compounds in the solvent. So we should be able to use thin layer chromatography to assess the purity of the product. So 3 different samples here, E, F and G. In E we get 2 different spots. So that means whatever E is, it's not a pure product because there's 2 different compounds in it. Whereas F, you've only got 1 dot, G, you've only got 1 dot. So in F and G, we've got a pure product. So having only 1 spot produced in the chromatography plate means we've got a pure product. What it doesn't mean, what that doesn't show is it's a pure product we're hoping to make. In order to determine that, we have to look at RF values. So we have to determine RF values from chromatograms. So the RF value is the distance travelled by the substance divided by distance travelled by the solvent front, which of course why we have to take the plate out before the solvent front reaches the top. So the distance travelled by the substance would be A, and the distance travelled by the solvent front is B. So the RF value would be A divided by B. We can then look up RF values in the literature and compare our RF value with the literature values and see if they're the same. Now, if the chromatography is carried out under the exact same conditions, the RF values won't change. In reality, what is more common to do is to run two samples at the same time. The sample you've made and a pure, some pure sample that you've got from the chemistry lab. So in A, say this is the aspirin that we've synthesized, and this is some pure aspirin. We can see that they won't have the same RF value. So what we've made in A, what we've made is a pure sample. There's only one product, but it isn't aspirin because it's got a different RF value. Whereas in the second run here, what we've made and our pure aspirin would have the exact same RF value. So that gives us confidence that what we've made is a pure sample of aspirin, and it's pure sample, and it is aspirin because it's got the exact same RF value as aspirin. And that, backed up with melting point and mixed melting point analysis, really proves beyond doubt that what we've got is aspirin. Finally, we usually do a calculation of our percentage yield. Okay. So we learnt how to do this in the higher, so it's the actual yield divided by a theoretical yield times 100%. And normally our yield be significantly less than 100%. So very often you're asked to explain or give a sensible reason why the yield is less than 100%. Often the reason is that the initial reaction is reversible, so you wouldn't get 100% yield. Also, sometimes you get side reactions, so your reactants, as well as reacting to give our product, there might be other side reactions that happen that produce other things and use up other reactants. And of course, transfer losses during isolation and purification procedures. So like if you're doing a solvent extraction, you will never get 100% of your product into the solvent. You always get some losses. If you're doing recrystallization in the filtration process, and you're always likely to have some transfer losses, bits of solid that you can't get off the sides of the book in a funnel, etc. So be prepared to explain why your yields are less than 100%. Okay, so there are the basic skills that we're expected to build up as you work through the experiments in the organic synthesis section of the course, and the things you should be able to explain in detail in the exam conditions.